Okay, for my lecture today, all I'm going to do is two example problems using conservation of mechanical energy. So you can see how this works, kind of what sort of problems you can use this for. Um, and I've mentioned before that really what you want to look for, if you're looking for a time that this is going to work better than Newton's laws, is you're looking for a case where first there's not going to be friction, and second, um, where what you're doing is exchanging information about an object's position for information about an object's speed. And if that's all you want, then it's worth it to take a little time to think about whether you can use conservation of mechanical energy for that problem. Okay, so the first example I'm going to do is one where we have an object attached to a cable. You can think of this as like um, a ball on a string, or a person on a swing, or anything like that. Um, and we're going to say that the radius of this circle, both of these examples I'm going to do with parameters instead of giving numbers. So we're going to get our answers in terms of the parameters that I've defined. But so we have this one parameter here, r, that's the radius of the circle or the length of the string. And then we'll say that the mass of this thing is m. We're going to see that in this example, m doesn't matter. So the answer is going to be the same no matter what m is. And the way we'll see that is that when we calculate our final answer, m will have canceled out of the math. Okay, so this object is rotating this way. And what we want to know is how fast does the object have to be moving at the bottom to swing all the way to the top? Okay, so if you picture something like this happening, uh, it makes physical sense. If you imagine swinging something really gently on a string, think of doing it like a pendulum. Excuse me, like a pendulum. If you don't swing it very hard, it's not going to make it to the top. But if you swing it fast, it'll swing all the way over the top and make it all the way up, so that the string is tight at the top. And so we want to see how fast we have to swing this object to make it all the way to the top. Um, okay, well, the first thing we have to do is think about what forces are acting, because we have to think about whether the forces acting, which ones are conservative, are there any forces that are non-conservative. In order to use conservation of mechanical energy, um, all of the forces that do work have to be conservative. So if there are any non-conservative forces acting, and that was in the lecture from last time, if there are any non-conservative forces acting, then those forces have to do zero work. What are the non-conservative forces that do zero work? The two that come up all the time are centripetal forces when something's moving in a circle. So in that case, in this example, the cable tension, since it's pointing toward the center of the circle at every instant, even though it's not that force is non-zero, there is some magnitude to that force, it's not going to do any work. And besides centripetal forces in circular motion, the other important type of non-conservative force that does zero work is normal forces when things are sliding or rolling along a surface. Okay, so I'm going to start by drawing a free body diagram of some representative instant. So we have an object here. Let's say that it's right at the picture I have drawn up above. So what forces are acting? There's a weight force. And then there's the cable force, T. And we have to think about, of all of these forces acting, those are the only ones, which ones are conservative, which ones are non-conservative. The weight is conservative, and that means that we know we have a potential energy function for representing that. So remember, the potential energy due to the weight is the mass times gravity times h, the height above some reference height, zero height that you choose. And now this one could be a problem because it's non-conservative. But in this case, since that's a centripetal force, it doesn't do any work. Okay, and that's all we care about for being able to use conservation of mechanical energy. All the forces that do work have to be conservative. Okay, so we're good. We can use conservation of mechanical energy for this. And so now all we have to do is set up two separate instants and calculate the potential energy, calculate the kinetic energy, and the sums will be the same at those two instants. Okay, so I'm going to call this instant 1 down at the bottom, and this instant 2 at the top. And I'm going to just set it up as a little table. Okay, so when it's at the bottom, we're going to calculate the potential energy and the kinetic energy. We always, for any problem involving gravity, we have to choose a reference height equals 0 location, and it doesn't matter where you choose it, as long as you're consistent throughout the problem. I tend to choose the object's lowest point over the motion, so I'm going to make this my height equals 0. Okay, so what's the potential energy due to gravity when the object's at the bottom? It's equal to its mass, m, times 9.81 meters per second squared, times its height, and at this instant we've chosen that to be height equals 0, so the gravitational potential energy is 0. And now the kinetic energy, what do we know about that? Well, the kinetic energy is 1/2 times the mass times the speed squared, and I'm going to call the speed at the bottom, that's what I'm going to call v. Okay, that's what we're going to calculate. So that's all the information that we need here. We don't have any spring potential energy because there's no springs in this problem exerting forces on that object. So this is all we have. Now up at the top, what do we know about the potential energy? Well, the potential energy due to gravitation is m times g times the height. If the height at the bottom is 0, what's the height at the top? Well, it's 2 of those radii. You know, it's the diameter of that circle. So we can write this as 2r, that's the h, times mg. And now if we're looking for the minimum speed that we can have at the bottom so that the thing makes it to the top, that means that it just exactly makes it to the top before, you know, it doesn't have any speed when it gets to the top. Okay, so it can't go any slower than v at the bottom and still make it to the top. Okay, so at the top, the speed is 0. And so the kinetic energy is 1/2 times the mass times 0, so this is 0. And now conservation of mechanical energy, the equation says add up the potential and the kinetic energy before, at that first instant, that has to equal the sum of potential and kinetic energy at the second instant. So we have 0 plus 1/2 mv squared is equal to 2r mg plus 0. And I said before I started this that in this problem, you're going to see that the mass cancels out. Well, now you see you can divide both sides by m. And so m just isn't a relevant thing in this calculation. And now we're going to calculate v in terms of these other parameters. So I'll multiply both sides by 2, and you get v squared is equal to 4rg. Take the square root, and v is equal to plus or minus square root of 4rg, which is 2 times the square root of rg. And we want the positive because speed is an absolute value. It's always positive. Okay, so what we got here is, if you look at the relationship, it makes sense that the bigger the radius is, the longer that string is, the faster the thing needs to be going at the bottom in order to make it up to the top. Yeah, that's about it for that example. One thing that I should say, so we're treating everything like it's a particle still. What that means in energy problems is that we're assuming that this object, the effect is that the object that we're treating as a particle, our answers are going to be wrong if that object is changing its orientation over time. So what's really happening here is, if you think of this as a person in a swing, this only gives a correct answer if the person's head is pointing up the whole way through. If the person's head is pointing up at the bottom and pointing down at the top, if you can imagine what I mean, then that's going to introduce a little bit of error into the calculations, and how fast their orientation is changing determines how much error is introduced. And so we can't do rolling problems and things like that accurately with this approach, but we can do sliding problems and things like that. I also should say that this is only true if we neglect any kind of friction, air resistance or anything like that. If there's significant air resistance, well, friction it's non-conservative and it does do work. And so that means that our assumptions that allow us to use conservation of mechanical energy are not valid. Okay, let's do another one. So for this one, let's say you have a spring attached to the wall, and this spring has a spring constant K, and it's attached to like a plunger thing, like at the start of a pinball game. And let's say that you pull it back, and when you let it go, it sends this cart thing launching out, okay? And let's say that it starts out along the flat and then eventually starts to go up this hill. And we want to know at the highest point it gets up the hill, what's that h? We're going to say again that this cart has a mass of m. And actually, we're going to do two things here. We're going to first, how fast is the cart going along the flat? So how fast is the cart after it leaves the spring. And second, how high up the hill does the cart get before it starts rolling back down? Okay. Well, again, with all these problems, the way to start to think about it is draw a representative free body diagram and figure out, what forces are acting. And I'm going to do two different ones because you can't really draw one free body diagram that's representative of everything here. So while the cart is in contact with the spring, the free body diagram looks like this. There's a weight force, there's a normal force, and there's a spring force. After the contact with the spring ends, that spring force is gone. So the forces you have are the weight, the normal force, and that's it. Okay, so now we have to think about what's conservative and what's non-conservative. The spring force is conservative, and we have a potential energy function for that. The weight force is conservative. There's a potential energy function for that one. The normal force is non-conservative, which at first makes you nervous, but the normal force for something that's rolling or sliding is one of those non-conservative forces that do zero work. And so the fact that work is equal to zero means that even though there's a non-conservative force, we can still use conservation of mechanical energy. In the second case, after it leaves the spring, the forces are the conservative force of the weight, the non-conservative force of the normal force, and again, the work is equal to zero. Okay, so first I'm going to do part A, where we're figuring out the speed while the thing's still along the flat. And then I'm going to do the second one that figures out how far we go. So for part A, our instant one is when the spring is pulled back. And our instant two is going to be right when it leaves the spring. And again, we're going to just set up this table, calculate the potential and kinetic energy at each of these instants. There's one thing that I left off in this drawing that we're going to need to know. We have to know how far you pull the spring back. Obviously, if you've ever played a pinball machine before, if you barely pull the spring back, the pinball doesn't go very far. If you pull it all the way back and let go, it goes really fast and really far. So this is going to depend on how far we pull it back. So let's say that the spring is pulled back a distance L from its resting length. Okay, that's how much it's shortened. If it went from If it started with a length of 10 centimeters and you pulled it until it was 7 centimeters, that L would be 3 centimeters. Okay. So the instant the spring's pulled back, if you look at that free body diagram, we have to deal with three things. Well, one of them we're not going to have to deal with because the work is equal to 0. And so we have two conservative forces that we have to deal with, the weight and the spring force. Okay, so the potential energy due to the spring force is equal to, and I gave this to you last time, 1/2 times the spring constant times the deformation squared So that's the potential energy that the cart has at that first instant. Now we have to deal with the weight force. The formula for this is mass times 9.81 meters per second squared times the height. And we have to choose a reference height, a height equals 0. I'll choose that to be at the ground. Like I said, I just always choose that at the lowest point that the object ever is in this motion that we care about. And so this is equal to mg times the height of 0, so 0 potential energy from the weight. And now the kinetic energy. That's equal to 1/2 times the mass times the speed squared. Well, we're assuming that when you pull this spring back, the thing is at rest before you let it go. So this is times the speed of 0 squared, and so there's no kinetic energy there. Now we have to do the same thing after it leaves the spring. But if you look at this free body diagram, now we don't have any spring force. So we're not going to have to deal with any potential energy due to the spring. We do have a gravitational potential energy. It hasn't changed height yet. We haven't gotten to the hill yet. We're just trying to figure out how fast the object's going along the flat. So this is going to be mg times the height of 0 again, so 0. But now we are going to have some speed, so the kinetic energy is non-zero. So this is going to be 1/2 times the mass times speed squared. And we're going to figure out what that v is in terms of the other stuff. Well, since none of the non-conservative forces do any work, we can use conservation of mechanical energy. And that says that 1/2 KL squared plus 0 is equal to 0 plus 1/2 mv squared. You can divide both sides by 1/2. And now we're just going to calculate v in terms of the other stuff. So v squared is equal to KL squared over m. Take the square root of both sides, and v is equal to plus or minus L times the square root of K over M. V is always positive, so we want the positive one. And so what this says is if you pull a spring back 3 centimeters and let it go, it's going to be going faster if, so let's keep that L the same for now. It's going to, so say it's 3 centimeters. It's going to be going faster if the spring is stiffer. That makes sense. It's harder to pull it back. It's going to make the thing go faster. If the spring is flimsier, then the object is going to be going more slowly after it leaves the spring. And it's also going to be going faster if the cart is lighter. It's going to be slower if the cart is heavier. Like if you use this spring to try to get a semi-truck in neutral moving, it would be, not moving barely at all because the mass is so great. Okay, so now we figured out what the speed is along the flat. Let's figure out how high the cart makes it up that ramp. We get the same answer no matter what we use as our instant one. We could use our instant one as when the spring is pulled back, or we could use our instant one as when the cart's moving with that speed v along the flat. So if you're trying to wrap your head around this stuff, you might want to try it the other way. But I'm gonna use the after it leaves the spring as instant one. And I'm going to use the high point on the hill as instant two. Because of this choice of instant one and instant two, the object isn't in contact with the spring either time, so we don't have to worry about the spring potential energy anymore. So after the object has left the spring, we know that, so we have to deal with the spring potential energy. Sorry, the gravitational potential energy. The spring potential energy we don't, because it's not in contact anymore. The height is 0, so this is 0. The kinetic energy is 1/2 times the mass times the speed squared. So we have 1/2 times the mass times this expression for v squared. So that's L squared times K over M. And the M's cancel, and you get a kinetic energy of L squared, let's say KL squared over 2. That's the kinetic energy. And then when it gets to the highest point on the hill, our gravitational potential energy is mg times the height of h. That's what we're trying to find this time, is that height h. And the kinetic energy, if it's at the highest point that it gets to on the hill, then right at that instant, the object has come to rest before it starts to roll back down. And so this is equal to 0 because v is 0. And now we can use conservation of mechanical energy. We have 0 plus KL squared over 2 is equal to mgh plus 0. And we're solving for h. And so h is equal to KL squared over 2mg. And so what that says is the farther you pull the spring back, the higher it'll get. The stiffer the spring is, the higher it'll get. The lighter the mass of the cart is, the higher it'll get, and so on. So I keep talking about pinball when I'm talking about this problem. Why didn't I draw this as a spring pushing a pinball? Well, when a pinball takes off, it's rolling. And so its orientation is changing really quickly. And like I mentioned in the first example, we can't do problems accurately where the orientation of the object is changing. We can't do it using conservation of mechanical energy because some of the energy besides speeding the object up, goes into making this object change orientation, makes it roll. And so this is true for a cart with very small, light wheels, but it's not true for a ball that's rolling. Okay, so that's two examples of how to use conservation of mechanical energy. So please send me emails with requests to talk about it, or with problems that you'd like me to do in the homework.